In this lecture, we'll discuss the asymptotic distribution of Ols estimators. Recall that in week 9, that's lecture 1 in the second part of the course, we introduced the linear regression equation, which looks like this. So y regressed on x1 to xk, these kx variables. So y is written as the linear function of these kx variables plus an error term u. We talked about the different interpretations of the linear regression equation depending on the research purpose. The research purpose including descriptive, causal, and forecasting, and that will determine how we interpret the coefficients and what assumptions we can make about the error term. The parameters, betas, we write it in a vector, beta vector, which is this vector composed of the beta parameters, beta 0, beta 1 to beta k. The beta parameters are unknown. Our interpretations are based on these unknown parameter values. So in order to make the model useful, we need to estimate the unknown parameters. And we introduced a sample that we can use to estimate these parameters. We introduced an IID sample drawn from the population distribution for which this population equation holds. And then using this IID sample, we can come up with estimators. The estimator that we talked about, which is not the only possible estimator, but that is the most commonly used estimator, and that is the ordinary least square estimator. So we introduced the OLS estimator. We spent lecture 3, I believe, or I think we spent lecture 2 on the derivation of the form of this OLS estimator. And in lecture 2, we derived that the OLS estimator for the parameter vector is equal to this, is the inverse of sum xi prime times sum of xi times yi, where remember xi is the x vector, is the vector 1x1 to xk if you have kx variables. So that is the formula for the OLS estimator. And in week 10, that is last week, we introduced conditions that guarantee the consistency of the OLS estimator. The conditions include these 4 assumptions. Orthogonality, which says that the error term should have expectation 0 and should be orthogonal, or in other words, has 0 correlation with the x variables. And the second assumption is IID sampling, meaning that the sample that we got for y and x variables should be an IID sample drawn from the population, that we are interested in. And the third assumption is finite kurtosis, which somehow is also related to large outliers are unlikely. So that assumes that this assumption restrict the y variable and the x variables to have finite fourth moment. And the last assumption we needed was no perfect multicollinearity, which says that none of the x variables is a perfect linear combination of the other x variables and the constant variable. So given these four assumptions, if these four assumptions are satisfied, we can show, and we did show, the consistency of the OLS estimator. So beta hat converges in probability to beta under these assumptions. And then we use the consistency result and use the Slavsky's theorem to predict, to estimate the prediction of certain conditional expectation of the outcome variables, including the gender wage gap, the conditional gender wage gap, given education level, and so on and so forth. We also discussed the consequence of misspecifying the conditional mean model. If we misspecify the conditional mean model, then we clearly don't get the correct form. We don't form the correct interpretation for the conditional mean function. And sometimes the misspecification cause inconsistent estimate for some parameters of interest. So that is a review of what we have done in the past couple of weeks. And today, we'll talk about asymptotic distribution. But why do we want to talk about asymptotic distribution? This is because consistency has, the concept of consistency has its limitations. Well, an estimator being consistent is good. Consistency is a good property for an estimator. It means that if you throw more and more data at the estimator, then the consistent estimator will eventually get close to the true value, get as close to the true value as you want, as often as you want, with as high probability as you want. But the key is eventually. So consistency is about what, how beta hat so eventually. So consistency is about the fact that the estimator will eventually get close to the true parameter value that you want to estimate as you increase the sample size. But the thing is eventually good enough? So the question is eventually getting close to the true value good enough? Well, I'm going to give you an example, and you can think whether that is enough or not. Suppose that you say to your girlfriend, I will eventually make as much money as this guy. Well, this guy, for those who don't know him, is the richest person in China. And clearly your girlfriend is probably not very happy about what you just said. So we need to go beyond consistency. It is useful to know that the estimator is consistent, but it would also be very nice to know other information. For example, we might also want to know at my sample size, say I have a sample size of 2000, at that sample size, what is the probability that my estimator is more than, say, 0.1 unit away from the true value? Just knowing consistency will not help you to answer this question. And for example, for another example, you might also want to know how much more data do I need to shrink that probability, so this probability, to a tolerance level that I can accept. Right? So suppose my tolerance for the probability that beta hat being 0.1 unit from the true value is 10%. So I cannot accept an error probability of higher than that. Then how large the sample size do I need? To answer those questions, we need to know the distribution. To answer those questions exactly, we need to know the distribution of the estimator at any given sample size. And we need to know how the distribution changes with the sample size. The problem, however, is we do not know the distribution of the OLS estimator. We know it is a function of the sample of the y and x variables, but typically we do not know the distribution of the sample. We do not know the distribution of the y and x variables. Even if we know some aspect of the distribution of y and x variables, beta is such a complicated function of them, it's not so straightforward to figure out the distribution of beta based on that. So what's the solution to this problem? The solution to this problem is asymptotic normal approximation. And let's recall from week 7, when the goal there was to estimate the population expectation of a scalar random variable z. Say the parameter of interest is just one parameter theta, which equals the expectation of z. And we want to suppose that we use the sample average as an estimator for the population mean, for the population expectation. So we use Zn bar to estimate theta. So we know if the sample is IID and if the variance of Z is finite, then this is consistent. The sample average is a consistent estimator for the population expectation. But suppose we do not know the distribution of Z, then we do not know the distribution of the sample mean. However, in week 7, we learned that we do not need to know the distribution of Z if we just want to get an approximation for the distribution of the sample average. The tool that we use is the central limit theorem. By the central limit theorem, square root n times the sample average minus the population expectation converges in distribution to a normal random variable with mean 0 and variance sigma squared. So that is root n Zn bar minus theta is asymptotically normal, which means that it's approximately normal when the sample size is big enough. And if this is approximately normal, this is a linear transformation of Zn bar, then Zn bar is also approximately normal at large sample sizes. So that means by the central limit theorem, the sample average, which is an estimator of the population expectation, is asymptotically normal, is approximately normal. Okay, it's approximately distributed by this normal distribution with mean given by theta and variance given by sigma squared divided by n, where sigma squared is the variance of the random variable you are interested in. And it's also equal to variance of zi because zi is a draw from the distribution of z. So this is a review of the material covered in week 7, where we showed, we demonstrated that central limit theorem can help us to derive an approximation for the distribution of our estimator. Here, we are going to be able to do the same thing for the Ols estimator, even though it's much more complicated because it's not a simple sample mean. So to see how we are going to do that, we start with the formula for the Ols estimator that we derived in last week. We start with this formula, and we want to use asymptotic approximation to get a guess of the distribution of this estimator, right? So we want to use asymptotic tools to approximate the distribution of this estimator. So how do we do that? The first thing we're gonna do is actually transform this into something that we can apply some version of the central limit theorem on. So what we will do is to subtract its population limit, or so subtract the true value or the probability limit of the estimator from the estimator. From the derivation of consistency in week 10, we found that this equation holds. So beta hat minus beta equals this matrix inverse times 1 over n sum of x and vector times ui, where ui is the error term. So remember how we derived this? I'm not going to go through that again. The way that we derived this is to realize that yi equals xi prime beta, sorry, not beta hat, but beta vector plus ui. Now, if you plug that in here, then the first term will yield this beta vector and the second term will yield this. So if you want to, if you don't remember, you can go back to week 10's lecture to have a review. So we derived that beta hat minus beta can be written as this matrix inverse times this sample average of x times u. Now, with this equation, what we are going to do next is to actually multiply square root n to both sides. So we multiply square root n to both sides. So we obtain root n times this difference equals this matrix inverse times the sample average of xu times root n. Then that's 1 over n times root n. That becomes 1 over square root n. So this is 1 over square root n times sum of xi ui. And this will be something that we apply the central limit theorem on. And this is why we want to create a 1 over square root n here. Because in the central limit theorem, we are applying, the central limit theorem is applied on 1 over square root n times a summation of IID random variables or random vectors. So now we will apply central limit theorem on this piece, but there is some complication. The complication is that this xi times ui is a vector instead of a scalar, so the previous central limit theorem that we learned doesn't apply. Now, pretend for now that x and bar is in fact a scalar, then this is a scalar, then this is just a one-dimensional random variable. We can define that to be vi. We define this to be equal to vi. Then we know this evi equals 0. This is by orthogonality, right? Because evi in this case would be exi times ui, and that equals 0 by a1, by the orthogonality condition we talked about when we discussed consistency. And expectation of that equals 0. So therefore, this is actually equal to square root n times the sample average of v minus e of v, right? Because e of v is actually 0, and v and bar, the sample average of v, is 1 over n times this summation, right? Now, because we have 1 over square root n here, so you can have a square root n here. Okay, so this purple term equals square root n times sample average of V minus population expectation of V. That is exactly something that we can apply the central limit theorem on, the one that we already discussed in week 7. And that converges in distribution to a normal random variable with mean 0 and variance that equals the variance of V. Right? So if we use sigma squared to denote the variance of V, then that limiting distribution should be normal 0 sigma squared. So if this is a scalar, then we can apply the central limit theorem that we talked about, we already have used in the first part of this course to show that this is asymptotically normal. But now for the Ols estimator, for this, in order to derive the asymptotic distribution of this whole thing, we ran into some complications. One complication, of course, is x is not a scalar typically. So this is typically not a scalar. And the second is that you got this piece also. And we need to deal with this piece too. How do we deal with both pieces together? And that's something that we want to solve as well. That's a problem we want to solve as well. So these are the two challenges. X is not a scalar in general, and this term also needs to be dealt with when we derive the asymptotic distribution. Fortunately, we do have tools to deal with both challenges. And the next thing we will do is to build the tools first. So with the right tool, anything is possible. So let's spend some time building the tools. The first tool we need is the vector central limit theorem. That is the central limit theorem, but applied to random vectors instead of just scalar random variables. What do we need for a vector central limit theorem? First, we want to review the distribution of a random vector. So what does the distribution of a random vector mean? Or in other words, the multivariate distribution. So what does that mean? And the second tool is the normal random vector. So we have talked about normal distribution for a single random variable. What is the normal distribution for a random vector? First, let's talk about distribution of a random vector. Consider a random vector of length m. So this is a column vector of random variables. And this vector is made up of these m random variables. So this z1 to zm, these are the m elements of the random vector. So z1 to zm, each of these z's is a scalar random variable. So z is a random vector. What is the distribution of a random variable, of a random vector? The distribution of a random vector can be described by, for example, a cumulative distribution function, the CDF. The CDF of a random vector is defined in pretty much the same way as the CDF for a scalar random variable. So the CDF of the random vector is denoted capital F sub Z vector evaluated at some value, a value that the z vector can take. Okay, so this little z vector is an element in the m-dimensional space of real numbers. Okay, so the CDF is defined to be the probability that the random vector lies below this value. Okay, this vector value. What does a vector lying below another vector mean? It means element-wise lying below. Right, so the capital Z vector being less than or equal to the lowercase z vector means this inequality holds for each element. Means the z1 is less than or equal to little z1, capital Z2 is less than or equal to little z2, capital Zm is less than or equal to little zm. Okay, so that is the definition of the cumulative distribution function of a random vector. So the cumulative distribution of a random vector may also be called the joint CDF of its elements. So the CDF of the random vector Z is also called the joint CDF of Z1 to Zm. Sometimes you might also hear people say the joint CDF of the random vector. So these terminologies all mean the same thing. And the notation, the mathematical notation for the CDF of the random vector may sometimes be written as this as well. So you might write the little z vector, the value you evaluate the CDF on, the value as z1 to zm inside the parentheses. Or you might sometimes even write the z vector, the random vector, in a subscript as z1 to zm also. So, which is only saying that the vector is not distinguished from from its elements. So in words, distribution of a random vector is the joint distribution of all of the elements of the random vector. And a function, so this is a function of a vector, is the same as the function of the elements of that vector. Okay, so a function of a vector is basically the function of all of the elements of that vector. There is no real distinction between the two concepts. All right, so that's CDF for random vectors. In the case where the elements of the random vector are continuous random variables, when we are talking about continuous random vectors, suppose that this cross partial derivative exists for the CDF, then this cross partial derivative defines the probability density function or joint probability density function of the random vector. Okay, so this cross partial derivative, where you take the partial derivative with respect to each and every element, each and every argument of the function. This cross partial derivative is the probability density function of the random vector, and it's denoted by the lowercase f sub z sub capital Z evaluated at lowercase z. Sometimes you write the vector in the function, the vector argument, as the m elements of that vector. Sometimes you write the z subscript, the vector subscript, as the m elements of that random vector. So these three things all stand for the same thing. Three notation stand for the same thing. All right, so now this graph shows you an example PDF for the case where m equals 2, for the case of a two-dimensional or length 2 random vector. For length 2 random vector, it's got two elements. It contains two random variables. Let's say this is the first element and this is the second element. So let's say this is Z1 and this is Z2. And on the vertical axis, here you got a 3D graph. So you got a horizontal axis, you got two horizontal axes, and you got a one vertical axis. This vertical axis is the probability density function. And this is an example of a probability density function. Now, let's talk about the second concept that we will use to introduce the vector central limit theorem. That is the normal random vector. Normal random vector is a special case of a general random vector. So multivariate normal distribution is a special case of other multi-dimensional distributions. The probability density function of a normal random vector looks like this. It's got a single peak and it goes down from the peak, just the way that the the one-dimensional normal distribution goes down from its mean. So this is an example of a normal random vector, but what exactly is a normal distribution in the multiple dimensional case? Now, to introduce that, we want to recall the normal distribution in the scalar case. In the scalar case, when you have only one normal random variable, say of mean 0 and variance sigma squared, the probability density function is of this form. It's 1 over square root 2 pi times sigma, which is the standard deviation of the random variable, times exponential minus z minus mu squared divided by 2 sigma squared. So we talked about this normal distribution before. Here, this exponential something, I think maybe we have talked about this before, maybe not, but this is e to the power x. This means e to the power x, where e is a mathematical constant that is approximately equal to 2.718. So for a normal scalar, so a scalar normal random variable, it's got two parameters, mu, which is the mean or expectation, and sigma squared, which is the variance. A multivariate normal distribution is actually quite similar to this form. A multivariate normal distribution, or the distribution of a normal random vector, Z, is denoted, the distribution of a normal random vector is denoted by capital N mu vector sigma matrix. Here, let's say Z is k-dimensional, then the mean vector is k-dimensional, and the variance matrix is k by k. So what is the probability density function of such a multivariate normal distribution? It is of this form. The probability density function of that random vector is of this form. It's kind of similar to the scalar case because if you look at what's inside the exponential function, you got a 1 minus 1 over 2 z minus mu times the inverse of the variance matrix times z minus mu again. Now, if k equals 1, then this is a scalar. Then you got a scalar z minus mu times the inverse of the scalar variance times z minus mu. and that would be exactly equal to z minus mu squared divided by the variance. And that gets you back to the scalar PDF form. Of course, in the vector case, you can no longer square these two because both of these are vectors. Instead, we take this quadratic form of the random vector with the inverse of the variance matrix as the weight. So it's not too important to remember this formula, but that is the formula for the multivariate normal distribution. And this parameter, mu, is the expectation of the random vector. And the sigma is the variance covariance matrix. And I will explain what I mean by variance covariance matrix. So sigma is the variance covariance matrix of the z vector, z random vector. And variance covariance matrix of a random vector is written as VAR parenthesis the random vector. Now, what's a variance covariance matrix? Let me explain that. Variance covariance matrix of the random vector is a matrix composed of the variances of each element and the covariances between pairs of the elements of that random vector. So as you can see on the diagonal of the matrix, you got the variances of each element. And on the off-diagonal term, say the first row, second column, you got the covariance between the first element and the second element, and so on and so forth. So that is the variance covariance matrix of a random vector. Just to give you a simple example, suppose that z is two-dimensional. The first element of z vector is x, which is a random variable, and y is another random variable. Second element of z is y. Suppose the variance of the first element equals the variance of the second element equals 1, and the covariance of the two equals 0.3, then the variance covariance matrix of the random vector will be 1, 1 on the diagonal, and on the off diagonal, you write the covariance. So that is an example of the variance covariance matrix of a random vector. All right, so now we are ready to introduce the vector central limit theorem. That is how you turn a non-normal random vector into a normal random vector by increasing the sample size. Okay. So what is the statement of the vector central limit theorem? We state the vector central limit theorem first. Let Vn vector I from 1 to n be a sequence of IID random vectors. So by now you should be quite familiar with this notation, right? So this is the short notation for the VI vector, the VI vector, is the short notation for V1, V2 to Vn, where V1 is the characteristics, the random variables for individual 1 in the sample, and this is for individual 2 in the sample, and this is for individual n in the sample. So let this be a sequence of IID random vectors. What this means is V1 is independent of V2, V2 is independent of V3, and so on and so forth. Across I, you have independence, and also the CDF of each random vector for each I is the same. So this is a sequence of IID random vectors, which means Vi and Vj have the same CDF, and Vi, Vj are independent from each other when I is not equal to j. So let mu be the expectation of Vi. It doesn't matter which I because they all have the same distribution, therefore the same expectation. And let sigma be the variance covariance matrix, and let the variance covariance matrix exist, meaning that it's finite. Then the vector central limit theorem says if you define Zn random vector to be equal to 1 over square root n sum of V vector minus mu, minus the population expectation, then that vector converges in distribution to normal. To normal with mean 0. The mean is a 0 vector, and variance covariance matrix given by the variance of the V vector. Okay, so that sometimes may also be written as the sample mean of the vector or maybe we should write Vn bar vector minus the mu vector. Okay, so that's root n Vn bar minus mu. Square root n times the sample average of V minus the population expectation of V. And that is analogous to the quantity we apply the scalar central limit theorem on. And the vector central limit theorem says that this random vector converges in distribution to a normal random vector with mean 0 and variance covariance matrix sigma. So that is the vector central limit theorem. So maybe a little bit of explanation is in order. So the random vector Zn converges in distribution to normal mu sigma can be equivalently written as Zn converges in distribution to Z naught, where Z naught is a normal random vector. So these two ways of writing the result is exactly equivalent. Okay. And what do we mean by converging in distribution for vectors? So what do we mean by converging in distribution for a sequence of random vectors instead of scalars? That simply means the convergence of the CDF of the random vector, or the joint CDF of all the variables in that vector. So convergence in distribution for vectors simply means the convergence of the CDF. All right, so that's the vector central limit theorem. And that's our first tool. The second tool we are going to need is the generalized Slavsky theorem, generalized Slavsky's theorem. So this theorem generalizes the Slavsky's theorem that we used to prove the consistency of the Ols estimator. So let me state the generalized Slavsky theorem first. Let Qn be a sequence of random matrices and Zn be a sequence of random vectors. And we're going to define a function g to be a function on Q and Z. Suppose that Qn converges in probability to Q0, where Q0 is a non-random matrix. And Zn vector converges in distribution to Z0 for a random vector Z0. And let G be a function on Q and Z that is continuous in Q at Q0, where Q0 is the probability limit of the Qn, and continuous in the second argument everywhere. So G has the desired continuity, let's suppose. Then the generalized Slavsky's theorem says G of Q and Zn converges in distribution to G of Q0, Z0. Right, so comparing to the Slavsky's theorem we used for proving consistency, there is some difference. The Slavsky's theorem simply says continuous functions preserves convergence in probability. And in the Slavsky's theorem, if you got a bunch of arguments, a bunch of random things that all converge in probability, you put them in a continuous function, then that continuous function also converges in probability. So, and there is no limitation to how many arguments you can put into that continuous function. Okay? The number of arguments in the function G is not limited to 2. So you can have 3, 4, 5, 6, and it doesn't matter. And as long as the function G is continuous in all of those arguments, it preserves the convergence in probability of those arguments. So that's Slavsky's theorem. For the generalized Slavsky's theorem, it's slightly more restrictive. It says continuous function also preserves convergence in distribution, but you cannot have an arbitrary number of arguments all converging in distribution separately and still claim G of those arguments converge in distribution. That's not true. Instead, the generalized Slavsky theorem only allows one argument, which could be a vector argument. Okay, only allows one argument to converge in distribution. It can have other arguments that converge in probability. Okay, so the number of arguments of the function G that converges in probability is not limited to 1, but the arguments of the function G that converges in distribution is limited to 1. Okay, that 1 can be a vector, but limited to 1 vector. Just to demonstrate what I mean, because this might be very abstract, I will give you an example. Let's consider an example of both the Slavsky theorem and the generalized Slavsky theorem. Consider a sequence of random vectors. You got Z1n and Z2n, both are random vectors, and also a random matrix AN. Let's say all three things, all three arguments converge in probability to some non-random limit. All three converge in probability to some non-random limit. And now consider the product of the three. Let's suppose they are conformable. This product is conformable, let's suppose. So the G function we are considering is this. The G function we are considering is this. And this function is clearly continuous in all three arguments. So this is a continuous function. Continuous function preserves convergence in probability by the Slavsky's theorem. And all three are converging in probability. Therefore, G of the three things, which is z1n prime an prime times z2n, that should also converge in probability to the limit, to the g with the limit variables or vectors plugged in. So g with the limit plugged in is z10 prime, a0, z20. Okay, so by the Slavsky's theorem, if you have these, then these hold. So this is fine. Now, suppose instead that z2n doesn't converge in probability, but converges in distribution to a random vector, not a non-random vector. So now z2n converges in distribution to a random vector. Now, the g function is the same as before. You use the same g function. Consider the same g function as before. Consider the same g function as before. It's still a continuous function. Now you got two things that converge in probability and one thing that converge in distribution. That's fine. That's allowed by the generalized Slavsky theorem. By the generalized Slavsky theorem, when you put these three things into the continuous function converges in distribution to the g of the limits of the three. Okay, so this holds by the generalized Slavsky theorem. The theorem applies because you got only one element that converge in distribution. The other ones converge in probability. Now let's consider a counter example where you cannot apply the generalized Slavsky theorem. I suppose that not only z2n converges in distribution, but also z1n converges in distribution instead of converge in probability. So now you got two arguments, two random vectors that converge in distribution separately, and an converges in probability. Now let's say the g function is the same. The g function is the same. It's continuous everywhere. Continuity is not a problem. But you cannot say g of the z1 and z2 and an converge in distribution to g of the limit. G of the limits of the three things. Okay. Now we cannot say this. This does not follow from the generalized Slavsky theorem because we have two arguments that converge in distribution separately, right? Not just one element, not just one argument of the function that converge in distribution. Now you can save this example if you can strengthen this separate convergence and distribution into a joint convergence. What that means is if you instead assume z1n and z2n jointly converge in distribution to z10 and z20. Or in other words, the large vector formed by the two vectors converge in distribution to this large vector formed by the limit of these two vectors. If this hold, and you consider the same g function, then you can save the convergence. Then you can apply the generalized Slavsky theorem to conclude z1n prime an z2n converge in distribution to z10 a0 z20. This is because now instead of having three things two of which converge in distribution separately. Now you actually just have two things. One of them converge in distribution. Only one big random vector converge in distribution. Okay, so for this situation, you can apply the generalized Slavsky theorem. All right, so now we have a toolbox that contains two very useful tools. One is the vector central limit theorem, and the other is the generalized Slavsky theorem. The vector central limit theorem says that if you got an IID sample of random vectors, then square root n times the sample mean of the random vector minus the population mean converges in distribution to a normal random vector with mean zero and variance covariance matrix sigma that is sigma equals the variance of VI vector. So that is the vector central limit theorem. What is the generalized Slavsky theorem? It basically says continuous function preserves convergence in distribution in some restricted sense. So it says if you got a Qn matrix that converges in probability to Q0, and Zn vector converges in distribution to a Z0 vector, where the Z0 vector is random. And let's say G is continuous. In Q, at Q equals this non-random limiting point of Qn, and in Z everywhere, then G of Q and Zn converges in distribution to G of Q0, Z0. And these two will be useful for deriving the asymptotic distribution of the Ols estimator. So now we have our tools. We can do our derivation. Now we're going to get back to the lovely formula for the ordinary least square estimator. In fact, we want to go back to this recentered and rescaled version of the formula. Root n times this recentered version of the estimator equals this matrix inverse times this random vector. Now we're going to let this matrix be Qn. So that's our Qn. We define Qn to be this. And we define Zn to be this pink random vector. So this is a random vector. For those of you who are still confused about why this is a random vector, that's because x is a k plus 1 by 1 random vector, and u, the arrow term, ui, is 1 by 1, is a scalar. So the product of the two is a k plus 1 by 1 random vector. That's for each I. Now if you add up n k plus 1 by 1 random vectors, you get a random vector that equals the sum of those random vectors. The sum of the random vectors is composed of elements that are sums of each element, okay, corresponding elements of these random vectors for each I. Okay, so what I'm saying is, say, just to give you an example, xi ui equals 1 xi1 to xik times ui, and that equals ui xi1 ui xik ui. And so how do you sum them up? When you sum them up, the sum of xi ui equals x1 u1 plus x2 u2 plus xn un. And that equals the vector that's composed of u1 plus u2 plus un and x1 1 u1 plus x21 u2 plus xn1 un to x 1k u1 x2k u2 plus xnk un. Right, so this is in fact this vector. Okay, just to give you an idea of what this is. Now that is that is defined to be Zn, and this is defined to be Qn. Then the quantity we are interested in, root n beta hat minus beta, is just the function of Qn Zn, right? So it's Qn inverse times Zn. If you define the g function to be Q inverse Z, then the quantity we are interested in is g of Qn Zn. Okay, so that's our continuous function. It is continuous in Z at any value of Z, and it is continuous in Q at any invertible values of Q. Now, we want to figure out the limit of Qn and Zn. We want to study the limit of Qn and Zn separately. Now let's study Zn first. Zn is 1 over root n times sum of xi vector ui. Again, to match the notation in the vector central limit theorem, let vi be equal to xi times ui. So let vi denote this random vector. From assumption A2, that's the IID sampling assumption, this vi vector across I is IID. So we got IID down, that's not a problem. And from assumption A1, orthogonality assumption, we know the population expectation of the v vector equals E of x vector times u. That is 0. That is a 0 vector. Now, you have two conditions required for the vector central limit theorem hold. You also want the finite variance assumption. So the variance of vi vector equals the variance of xi vector. So it's xi vector times ui. This is guaranteed by the finite kurtosis assumption, assumption A3. And for those of you who want to know why this guarantees this assumption, I will just show you a very brief derivation of it. So the variance, this variance covariance matrix, let's only show the finiteness of the first element. Maybe not the first element, but the second element, second diagonal element of that. Second diagonal element of sigma is the variance of x1i ui. And the variance of x1i ui equals expectation of x1i squared ui squared. Why? Because the expectation of x1i ui equals 0. So variance of that equals expectation of x1i squared ui squared. And that I will state, but without proof, that this is less than or equal to the square root of e of x1i to the power 4 and times expected value of expected value of ui to the power 4. And the finite kurtosis assumption will say that this is finite. The finite kurtosis assumption will also imply that this is finite. Okay, the reason is so to show that you're gonna also need to realize that ui is yi minus beta 0 minus beta k x k to the power 4th. And if you expand all of this, you use some kind of inequality, you're gonna find that this is less than or equal to a constant times expected value of yi to the power 4 plus expected value of xki to the power 4. So these inequalities I will not explain, but these are some mathematical inequalities that we use a lot in proofs. But this simple sketch of the derivation will show that our assumption of finite kurtosis will imply the variance covariance matrix is finite. Now we have all three conditions that are needed for the vector central limit theorem. We can apply the vector central limit theorem, and that's going to tell us that the 1 over root n sum of vi converges in distribution to a random vector z0, where z0 is a normal zero variance xu. Okay, so z0 is a normal random vector with mean 0 and variance covariance matrix equals the variance covariance matrix of vi, which is the variance covariance matrix of x times u. Okay, to sum up, we have proven that Zn vector converges in distribution to this normal random vector. And in lecture 3, after the midterm, we have also shown the limit of Qn when we derive the consistency of the Ols estimator. And the probability limit of Qn is Q0, which equals expected value of x times x prime. And this matrix is invertible by A4, by no perfect multicollinearity assumption. So now we have used all 4 assumptions. So the limit of Qn is invertible. Therefore, the g function that we defined, g equals q inverse times z, it is continuous in q at this limit point of Qn, and it's clearly continuous in z at any value. So therefore, we can apply the generalized Slavsky theorem to conclude that root n beta hat minus beta converges in distribution to g of q0 z0 vector, which is q0 inverse z0 vector, where q0 is expected value of x x prime, and z0 vector is normal with mean 0 and variance x u. Okay, variance that equals the variance covariance matrix of xu. So that is the conclusion. So root n beta hat minus beta has this limiting distribution. Now, we will not talk about what this limiting distribution exactly is, but I'll just give you a preview. This is going to be a multivariate normal distribution. We would derive the exact formula for the variance covariance matrix and the mean of this multivariate normal random vector in the next lecture. But now let's just stop here because we have derived the asymptotic distribution of the Ols estimator. So it's going to be asymptotically normal. Okay, so that's this lecture. And the last few pages of these slides, you might find useful if you're not used to the notation of random matrices. So these slides will break down the notation of random matrices for you. It might be helpful. So I will not go through that in details.